Okay. All right. I hope you've all looked at the homework, and if you have questions about it, you should come to me or see your GSI. It's only got to be an estimation problem. Take a look at what's involved. For example, you can estimate how big a solar plant, how big does a solar plant need to be? Okay, this is a picture, a montage of the moon. It's random. I just put this up. This is let's see. What's done? Oh, great. Oh, yeah. What have I done here to my computer? Come on. Okay. All right. All right, we're going to talk a little bit about the history of astronomy now. The history of astronomy parallels the birth of science as a scientific method. People are not born with any thought of how they should think. Scientists had to develop over the years, and it took a while to understand how science is done. And this is a lesson you should all understand. Particularly, you can read Helen Quinn's article. I'd like you to look at that and see what she has to say. Okay, here is the heavenly sphere. Here's the Earth and the planets surrounding it, the moon, the sun, all these planets was put on it. This is all thought of how it worked. Now, Plato wrote of the way you do things, and he had a work of the mind for philosophers. Philosophers were known as scientists in those days. There wasn't any distinction between a philosopher and a scientist. He is the brilliant, or the people who didn't have anything else to do, who were the philosophers. Working on the hand, raising the crops was the work of the slave. Now, Aristotle came around at the same time, and he has a great system of the world. Okay, how does this world work? Separates heaven and earth, perfection of the celestial sphere. So everything moves on circles and is perfect. At that time, they understood how a circle worked, and they thought, well, the sky is celestial, is perfect. Okay. Gravity is attraction for terrestrial matter. He knew that much. But he understood phases of the moon, rotation. He knew that was rotation around the Earth. And he realized the Earth is round. How do you know the Earth is round? Because it will cast a shadow on the moon during an eclipse of the moon. The sun shines on the Earth. You see it's a round object when it casts its shadow on the moon. So that was nice. And that conformed to his prejudice. All right. And he also knew that as you go north or south, you can see different parts of the sky. So he understood that was what you would expect if you're living on a sphere. Okay, so that much he understood. Now, he knew also that to understand the universe, you had to think of the two possibilities. One, that the Earth rotates. Or two, the sky rotates. All right? Now, he chooses the heliocentric cosmology, sorry, geocentric cosmology. Geo meaning Earth at the center. That was his universe. The Earth is at the center of the universe. Now, as opposed to heliocentric, meaning the Sun at the center of the universe. Now, he knew, because he can't see parallax of distant stars, which he assumed you'd be able to see as you look in different directions, or you look at different months, he couldn't believe that the stars would be so far away that they wouldn't see parallax. So he assumed that this proved the Earth is geocentric. Okay. All right. Now the problem was that he used words, not observations, and this appealed to the medieval mind and developed. This retarded the development of the science. So that was how science was done. Nobody knew any better. Nobody knew any better at all. All right, so this is what he expected to see. Here is a nearby star. Okay, put it further away, and the parallax of it and against the other stars in the background is, here's a big one. Here large, now small when it's farther away. This is what you saw in the problem set that's due this week. You could just use distant stars as a tableau on which you see the parallax. But we don't see parallax of distant stars. So he assumed the distant stars are a painted tapestry. Yes. Parallax is what you see when you look at different angles, like look at your finger. And you see that behind the finger, I'm looking at that student there, you see a different view, right? That parallax is how we judge distances. The human eyes see the parallax of distant views and judge distances from that factor. So that is how it's done all the time. Now he knew that, and he can't see parallax of distant objects, even though here is a case. He knew that if the Earth were geocentric, I'm sorry, this is heliocentric model, the Sun in the center, and the Earth rotating around, and so 6-month interval, here's 1, 6 months, down here. So he would expect to see that the view from the distance of the universe would be very different if the stars were out in space. So he assumed instead of that, the stars are painted on the sky. And the best view is the geocentric cosmology. All right, that's what he expected to see. He didn't see it, obviously. Okay? Now, go back. All right, this is a view of a lot of stars. This is actually a view if the stars were 100 times closer to us than they really are. You would expect to see them moving. This parallax should be effective. But you can't see, they're so much further away you don't see this. So the stars that are moving are closer. The stars that don't move are further back. And you see the parallax just like you see on your eyes. All right. Aristarchus, a little bit later, he knew that the size of the shadow of the Earth on the moon when the eclipses are right. You've all seen a lunar eclipse, I presume, right? Okay, see its shadow. He judged that the Earth is 3 times the size of the moon because the curvature of the Earth was 3 times that of the moon and looking at it. So the modern value is close, it's 3.7. He also knew that a total eclipse is just possible That is to say, the angle of the moon in the sky is about the same, very close to being the same as the angle of the sun in the sky, and that's half a degree out there. Okay, that's about half your thumb width when you stretch it out. All right, he knew that was the same. Now he knew also that similar triangles would lead you to distance of the sun over the distance to the sun over the radius of the sun is the same as the distance of the moon or the radius of the moon. Now he knew that from his geometry class, which he took in high school. And then you just solve this equation, and the distance of the sun is equal to distance of the moon, radius of the sun over radius of the moon. Now he also thought, well look, here's the sun, it's out here, and he's going to time the distance between first quarter and third quarter of the moon. Now, he figured correctly that the moon is, it is just like this. The sun shines on half the moon, and we see it exactly half illuminated. So that's the first quarter moon. The third quarter moon is just the opposite. So he estimated that this angle is not 180 degrees, it's a little less than that. His estimate was that the radius of the moon over the radius of the sun is 1/20th. The distance of the sun turns out to be larger than the distance to the Earth. And because it's larger than the Earth, it should be the center of the universe. Anything that's biggest should be the center, he thought. Now, this was highly criticized. People just criticized him for being impious. They didn't care what his theory told him. So, they're not scientists. There are no scientists in the world at this time. So, well, that's ridiculous. It's just wrong. But in fact, it is okay. That actually works. It turns out that he has the right idea, but the sun is 100 times the size of the Earth. And this effect is very small. Theta is actually very close. Theta is very close to pi over 2. Okay? By the way, do you all know the use of pi over 2? Pi over 2 equals 90 degrees, right? You know all that. You learned that in high school. Okay. Now, Eratosthenes was a little later still, and he noticed that if you look at a sun during the sun is, you can look at the sun and see all the way down a well. Boy, what's the matter with this thing? All right, you can see down a well, perfectly down a well. Here's a well, and the sun rays go all the way straight down the well. But he knew on the same day that you take an obelisk in Alexandria, and you measure, is it straight down the obelisk, big point, and it was not quite straight down. It cast an angle here of 7 degrees. All right, so he knew that playing geometry, he knew that the radius of the Earth would be determined by this observation. He knew, he called it a distance. I don't know where he got this number or what it is. 5,000 stadia between Alexandria and Cyrene. Okay, then that means that the circumference of the Earth turns out to be 360 over 7 degrees here, times 5,000 is 257,000 stadia. So he measured the size of the Earth. The problem is nobody really knows what a stadia is. Okay, that technique is fine. It works. Okay, Hipparchus. He played a role. He made star catalogs. And he noticed that the Earth precesses. The Earth spins this way, but the spin axis actually moves. Right now, the North Pole. Right now, the North Pole is very nearly pointing at the star Polaris. But 23,000 or in 10,000 years, it's going to point someplace completely different. And we will not be able to guide by going to Polaris. Okay? So Polaris is an accident. He had very refined measurements, and they're beyond the other people. He measured the length of a year to an accuracy of 6 minutes. And he also measured that the sun orbits the Earth in an irregular fashion. It was not completely fixed. For example, he knew this quantity. These are pictures. This is a picture, a modern picture obviously, of the time interval between days every other week. Okay, the days are measured with a clock, a modern clock. So you wait a day, and you see that the sun has a figure like this. It's very strange. This strange figure is called analemma. Don't worry about what it is. Analemma is the name of this figure. You've seen on globes, old ancient globes that they used to have. I know I had one at home. Has analemma drawn on it. Has anybody else seen? Anybody else got a globe where there's a figure? Yeah, there's one. That's what it is. Okay? The motion of the sun is not regular. And this was very strange. And it turns out that this is expected in an elliptical orbit. The sun, the Earth, does not actually fit a circular orbit around the sun. Nobody knew that at the time. But he did know that the sun did not describe a perfectly regular orbit. Okay. You know, this is really stupid. This is it. Yes. I just moved the batteries. I think I got to deal with corrosion on the battery cable. Okay, so here's the precession of the Earth. The Earth is just like a top. You spin a top, and it doesn't always spins like that, but it actually rotates around. You've all seen that if you've ever spun a top. That is called precession. Okay? That is caused by an angular momentum, conserved angular momentum, and it just does that. The Earth does the same thing. Right now it points to Polaris, 15,000 years. It'll rotate around, and it'll point to Vega. All right, so that is exactly what happens to the Earth. All right, so the Greek scientists, philosophers, you know, they were influenced by Pythagoras, as you were in high school. He taught you the geometric method, the perfection of circles, spherical heavenly bodies. This is what you learned. You learned about all this trigonometry, right? I learned that in the 10th grade. I don't know how old you were. Is that when you learned that stuff? Okay, 10th grade. Is that right? 10th? Oh, well, okay. You're such an advanced high school. Mine was a dumpy high school. Okay. All right. Now, this is not based on anything other than they have no evidence for this. This is based on, not based on reasoning. All right? They assume the spherical motion is perfect. Therefore, the planets have to move on a spherical circle. End of story. That's how it was. There's no scientific evidence. All right. The modern method is to find predictive ideas. You have to look for them. All right, now let's see how that might have happened. Okay, Ptolemy was the last Greek astronomer, 140 AD. Now, he codified a geocentric cosmology, and he wrote a book that was very famous and passed on later generations, called the Almagest. This survived until the 17th century. 1400 years. All right, or 1700 years. Okay, that is pretty good, or 1600 years. Now, he observed the data and he tried to fit it with circles. And it turned out to fit the data accurately, he needed 80 circles in the solar system. Now, what the hell, what kind of model has 80 free parameters in it? No reason for them, just 80 free parameters. All right, and this is a predictive tool. It's not necessarily a reality. It predicts the position of planets, and this was adopted by the Catholic Church. Remember, in the early part of after the Roman Empire, the Catholic Church was dominant, and there were no alternatives. Okay, so this was the belief that everybody had. I told you about Dante's picture of here's the earth and paradise with these circles of everything out there. Heaven's up here, hell is down here. Okay, that was the world of Ptolemy. All right, now how does what does this mean, a circle within a circle? So here's the earth at the center of the universe. A planet goes around, but the planet's not really on this circular line. It's not really on this line, the orbit of the planet. It's actually on a smaller orbit. It's doing loop-de-loops on the smaller orbit, and this is necessary because you have to explain why the planets take loops. They knew that planets take loops. So one way to do it is to just say, well, the planet moves on loop-de-loops and goes around the sky. All right, and okay, fine. Okay, that's what you need. All right, now, this was accepted, and the method, the book was preserved by Arabs and Irish. I don't know if you can read something about how the Irish were scribed. The Irish church was scribed. They were quiet up there. They weren't affected by all the wars in Europe, and they copied the books over. Remember, they didn't have a Xerox machine. They had to copy a book by hand. There are a few copies in the world. Of course, there wasn't a printing press either. It's amazingly different. But King Alfonso said, boy, oh boy, 80 circles in the universe. I mean, how the hell does it need so many? He advised that the creator should have used a simpler scheme. This scheme, Ptolemaic scheme, is way too complicated. So he said, well, why isn't it simpler? Now, there's somebody called Occam, 1340, and this is his quote, although it's not really Occam who made it up. Somebody else did, I can't remember whom. But this is quoted as something he did, and really is somebody else. All duplicity ought to be posited without necessity. In other words, simplest is best. So this is not a simple theory. All with so many circles, it's a bit crazy. All right. Now, these predictions got to be pretty bad after a while. You could see a few degrees accumulation of the predictions of Ptolemy, and so people knew it wasn't so good. People who thought about it, but most of the world didn't think about it. Okay, now then comes Copernicus. This is all the birth of scientific method. Copernicus looks at the sky. All right, and he publishes a terrible book.
This place. This noise is right there. Give that a shot.
Okay, yeah. Okay, is that all right? Okay, so Copernicus, he assumes circular orbits as well, so it's not that good. But he gets the number of circular orbits down from 80 to 30. Well, that's better, but still, why do you have these circles? All right, so he didn't know an answer to that. He said, look, it's a little simpler theory. It's probably better than the geocentric cosmology. All right, but it does provide a natural explanation of the retrograde motion of the outer planets. That was the key. The retrograde motion is when the planet goes backward. Okay, now he just posits, he knew about the stellar problem, and he said, well, the stars are far away, very far away, because otherwise they'd have parallax that we can observe. People didn't understand that either. Why would the stars be so far away? Okay, he argued for heliocentric because it's not as complex and it's more beautiful. But, and you know, this is how it works. The planet would move back and forth, all right? And that's the stellar parallax that he knew. Everybody knew how that worked. Okay, now, unfortunately, the Roman Catholic Church disapproved. In those days, the church took a view on scientific theory. They didn't distinguish between science and religion. And they thought he's irreligious, he's bad for positing something that's different from what we've accepted. That's all it amounts to. All right? The Protestant religion was just as bad. Protestantism was coming into its own. Europe would descend into 30 years war, followed by another 40 years war, followed by 100 years war. All these wars all the time. It is amazing. You know, we talk about long war in Iraq. That's nothing compared to the 30 years war. Okay, Luther, founder of Protestantism, he called Copernicus a fool. All right, and at the end of the century, he was severely repressed. Okay, and the church corrected the book, removing 9 sentences, and he says, it's okay now. You just cross them out. Okay, and this was how they acted. Nowadays, religion. Nowadays, I've talked to the Pope. I went to a conference at the Vatican. They've learned their lesson. They don't get in the way of scientific theories. Okay, they're quiet. They accept it, and he knew that science tells what the universe does. Okay. Astronomers, it wasn't obviously better as a tool, so they didn't really accept it. Okay, Tycho Brahe, king, that he should give him a lot of land and a lot of serfs, workers. He had all the serfs on an island outside of Copenhagen, and they worked for him, and he built a big telescope. Now, they didn't have optical telescopes. This is a telescope that is really a giant protractor. You know those toys that you used in 9th grade and 10th grade for measuring, for doing all kinds of stuff, drawing circles? Okay, well, he had a big one that you could really use and set accurately. You know, might with an arm maybe up to the corner. It was really big. Okay? And so he used it and set very precisely what it did. And he was able to measure, I think he measured it to distances 1 arc minute. 1 arc minute is very, very difficult to measure with a protractor. It's really hard. You know, a protractor you can see is divided up into 0 to 90 degrees, but a minute is only a fraction of a degree. So it's very hard to do that. So he had a big protractor. All right. He also was a womanizer, drinker, and he lost his nose. This was crazy. You know, people would have dual smirched, and they'd fight it out with the nobleman who challenged him, and he lost his nose. You know, a lot of people a lot of noblemen lost their nose, and it might be sliced off, half of it gone. And I've seen one in Italy at a small town up on a mountaintop where all the pictures of him, this is a woodcut, beautiful woodcut, which means it's a different type of wood inlaid in wood. Very pretty. all the woodcuts were taken from the side, where you couldn't see his nose was cut off. So all pictures over there. You know, that was how they did it. Other noblemen would wear gold noses or wooden, I don't know, some sort of nose to cover it up. All right. That's a different world. All right, now, Johannes Kepler was basically a graduate student who worked with Tycho, and he inherited all of Tycho's data. Tycho eventually died. He got sick and died. You know, he was Tycho was next generation. Kepler was next generation, and he spent a long time, basically spent his life, trying to understand the orbit of just one planet, Mars. And he showed that Mars does not describe a circle. It in fact describes an ellipse. Now, in high school, you learned that if you use a pencil that's pinned to the center here, and you could pull the string tight and draw around, and you describe a circle. A circle is something that has constant radius. Now, if you want to draw an ellipse, you use two foci, here and here. The string is fixed, the total string length is there, and as you move around, it goes more here, less here. And you draw an ellipse. Okay, if the foci get close together, it goes into a circle. All right, so here's a circle, here's a moderate ellipse, here's a big ellipse. All right, so Kepler scratched his head trying to understand the orbit of Mars, and eventually he said, well, let's try an ellipse. He couldn't make it fit. It was not fitting to anything. And he was amazed, elliptical orbit about the sun fit. So this told him that, my gosh, a circular orbit is not right. Oh my God, what am I going to do? All right, this is terrible to give up the perfection of the circle. That's what he was brought up with, a religious bringing. All right, the orbit of all the planets is pretty close to circular. It's not very far away, but it is elliptical. The Earth is elliptical in its orbit. Okay, it only changes by a few percent between closest and furthest. It's not a big deal. Okay, and you wouldn't even observe it. All right, now here's what he also noticed. That, first of all, there's a couple terms you need to know. Perihelion means closest to the sun. Aphelion means furthest from the sun. Now, let us draw this triangle, say a month. This is a month's orbit. Another month, 6 months later. He didn't know why, but he noted that when you're close to the sun, you move fast. When you're far from the sun, you move slowly. Why is that? Who knows? He had no idea how to explain that, but he observed it. All right. Now, his first law is that the Earth moves in an ellipse. Sun's at the focus. Okay. The second law is this business about how it moves when it's close. It moves fast when it's close to the sun, slow when it's far away from the sun. But it moves in a way to allow this angle to be the same. And the third law was that the square of the planet's orbital period proportional to the cube of its semi-major axis, and we'll go into that a little later. Okay, now this is something what he observed was that this is the period of the planet, say the period of Earth, and the distance of the Earth to the sun. We could say the period of the Earth is 1 year. Distance of the Earth to the sun is 1 astronomical unit. 1 squared is equal to 1 cubed. All right, that's fine. That defines Mars, or the period of Venus, and it works out perfectly for all of them. He had no explanation of any of these theories, but he reported them. So he reported data, real data, that needed an explanation. All right, and this data, but then you no longer needed helios, you no longer needed his eccentric circles and all that other stuff. This is it. Everything's described by that theory. So, boy, that's pretty impressive. Okay, why does it work so well? He scratched his head and never figured out why. He died, and it just went into the literature, and he never had an explanation for how to explain these laws. But he did observe them, and people learned about it. Okay, then came Galileo. All right, Galileo was the first to build astronomical telescopes, and he saw, for example, Venus. Here's what he saw for Venus. It shows the same sort of half moons that he saw for the Earth. It was half moon one way when it's on one part of the sun, half moon the other way when it's on the other part of the sun. Obviously, this is proof that the heliocentric cosmology is right. But he needed a telescope to do it because he couldn't see Venus as anything other than a point without the telescope. Okay. Oh, well, that's supposed to go away. Hello. Oh, okay. All right. So this supported Copernicus, the motion of the phases as it orbits the sun. He discovered 4 moons of Jupiter. This is something you will be able to see when you use our telescopes. It's really quite beautiful. The moons are in different position around Jupiter. It's very pretty. And he looked at the Milky Way. He saw sunspots on the sun. He measured the rotation period, but he went blind in doing, almost blind. He had a bad idea. He was the first one to use a telescope. He did not invent the telescope. He heard about somebody up north, I think in Holland, invented a telescope, and he built one for his own use. Okay? Now, this looking at sunspots on the sun was very dangerous. Nowadays, we don't look at the sun directly. Please don't ever look at the sun directly, because you'll go, the telescopes are better and you'll go blind. Don't do that. We now can have the sun, the focus from the sun is cast on a piece of paper, and you can see that piece of paper, reflected light from it. You can see the sunspots. Usually. Sunspots are pretty prevalent now. Okay, he saw mountains on the moon. Remember that these are heavenly bodies, and they're supposed to be perfect. That means they're circles, and they don't have anything on them. No mountains. That's terrible. So they weren't heavenly bodies anymore. And the Catholic Church didn't like him either. He was forced to recant. I don't know if any of you have read the book Galileo or books about him. There's a play and other stuff. He had a tough life. Catholic Church kept him in house arrest, and they would have burned him. They burned one of his predecessors, I think Bruni, because he said stuff that wasn't considered acceptable. Now, this is only, 1500? 500 years ago. They're burning people for what they say. The scientific method was not accepted in the world. It was challenging religion, and it must be wrong. Scientists were slowly waking up and saying, hey, listen, you can believe what you want, but really the universe does something else. Okay. Here's his notebook. Very nice notebook. Here's Jupiter with its planets orbiting. 1, 2, 3, and sometimes the planets aren't visible. They're behind Jupiter. Here's 2 and 1, 3 and 1, etc. And he saw, gee, this is just like the solar system we expect. It's a miniature solar system. I mean, it's a moon, it's a big planet with its moons orbiting around it. this is more thought that the heliocentric cosmology is right. Okay? Because here's examples of it. Here it shows 4 moons down at the bottom. Okay? And those are the number you'll see. Maybe. Okay, Galileo, he also did experiments. He invented laws. He saw laws of inertia. Body at rest stays at rest. The body in motion stays in motion unless acted on by a force. Linear momentum is constant. This is the force times the mass times velocity unless an outside force acts on it. These are laws that he built apparatus. He built an inclined plane, and he did the experiments and cast what he saw in terms of laws. Okay, Aristotle was contrasting it, and he said, Aristotle said, a body seeks its own speed. I don't know what that means, but a fast body moves fast, a slow body moves slow. I'm not quite sure what it is, but that's what he said. Now, he had no evidence for it. He just pronounced it. A typical philosopher. He didn't have any backing for it. But the Catholic Church believed it. But the very famous thought experiment at the Tower of Pisa, have any of you seen the Tower of Pisa? That's the famous one that's leaning. I guess it's leaning quite a bit because it's underneath this foundation. It's sand, and it leaned. It would have crashed a long time ago, except people went in there and stiffened the foundation so it doesn't move anymore. Okay, now this is a thought experiment, and that is to say, you do the experiment. He didn't really go up to Tower of Pisa. I think it's dangerous to go up there. But you go up there, and he takes a ball, drops it. He sees an acceleration, 9.8 meters per second squared. That's what we call little g. He takes another ball, say a cork. One was steel or lead. Next one is cork. And he sees exactly the same acceleration. Exactly the same. And that's, of course, contrary to Aristotle's conjecture, Aristotle's belief. Okay, there is independent of any property of a falling body. It's independent of its mass, size. Now, this is only accurate if you can really ignore air friction. Okay, so you take that away. You do this in a vacuum, and it works. In fact, okay, so let's look at what happened. You go up to the top of a tower, Acme something. Okay, you let go of a ball, and at time t equals 0, the velocity of the ball is 0. At time t equals 1 second, the velocity is 10 meters per second. At time 2 seconds, it's equal to 20 meters per second, and it goes. That's the velocity. That's the acceleration of a ball. And that's what Galileo understood. And this acceleration is completely independent of what the ball is made of. Now, people have tried to do experiments and check to see that the acceleration is the same, and is the same to a part in 10 to the 15th, 10 to the minus 15th. I mean, it's very accurate. It's exactly the same. We can't find any difference. Okay. All right, now Christian Huygens realized that even a body moving in a circular orbit, say here, it's changing. It's moving first this way, and then it moves here. Later it'll move here, 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 and here. He realized that an acceleration is necessary to do that, and the acceleration is v squared over r. Don't worry about that. I'm never going to ask you that. But the body is accelerating if it's moving in a circle. So that's important to realize. All right, so along came Newton. Now, what did Isaac Newton have to say about this? Here he realized, he thought about this very hard. He wrote books, wrote a book, Principia, that talks about this discovery. He is the first really brilliant physicist. He is a very, very smart man. And he realized that momentum is a product of mass and velocity. Momentum is velocity has a direction, so it's a vector. Now, you haven't learned vector calculus, I don't think. Does anybody know vector calculus? All right. Well, a vector means a velocity is going this way. It's not the same as a velocity going that way. Velocity, the directionality is important. All right. Well, Newton understood how to do this. All right. And he made this simple idea. Force is an object for change. And finally, gravitation, he realized, is universal. And the law of mechanics is something that unifies heaven and earth. And he realized as well, this is the first realization of this, that the mathematics was the exact way to describe the universe. You had to have mathematics to describe it. God worked by describing mathematical laws. And that's it. Okay? And he came up with a clockwork universe. Now, how does this work? Okay, the Principia has three fundamental laws of mechanics. First one, Galileo, this was Galileo's law, conservation of inertia. An object is moving straight, and it's going to continue moving straight unless something is stopping it or pulling it off to the side. Okay? Newton says that next law, forces do act on the body. Linear momentum changes, such as force is equal to mass times acceleration, F equals ma. That much you've, who's seen this F equals ma before? All right, everybody's taken physics. This is Newton's second law. All right, and in honor of Newton, the force is in units of newtons, and it has the units mass times acceleration. And Newton's third law is that momentum is conserved. If you have momentum here, momentum there, it has to be equal momentum backwards. That's the principle by which rocket engines work. The ship goes accelerating this way, and that's only because it's spewing out hot gases the other way. And one's pushing around, okay? So this was his law. Okay, now, he realized that he was thinking, there's a famous drawing of Newton sitting under an apple tree, and he gets conked by an apple falling on his head. It's the same force as the moon orbiting the Earth. Now, how does that work? He spent many years, and he had to invent mathematics to do it. He invented calculus at about this time. All right. He needed this to form what the heck was going on. All right. And, all right. The law he eventually made is this. Force is equal to the mass of one, mass of the other, divided by the distance between them squared. This you've seen in mechanics course. This universal law of gravitation is something Newton made up. He didn't like it. He didn't say it was right. He didn't understand why an r squared was here and it wasn't r to the 2.1 or 2.2. He never understood why it was that way. He just said, I have to do this. I don't know why. I don't know why. It's an inverse square force. But it is. And he did not explain that, and it was not explained until Einstein came up with a theory to explain it perfectly simply, and we'll talk about that a little later. Okay, but one of our squared force was considered right. Okay, so Newton's, these are the units, put it in. Don't worry about G. I will never ask you what G is. Do not worry about it at all. In fact, do not worry about any mathematics. Okay, this is exactly the same as the law affecting electromagnetism, or light. You shine light at an object, it gets bright, but if you move the light twice the distance away, the brightness it shines on an object goes down a factor of 4. Same inverse square law. Okay, action at a distance was incredibly strange. Why should the moon or the sun act on the Earth a good distance away from it? And why in the world does it act at a distance? What is it about the sun and Earth that makes them attract each other? He could not explain that. And nobody could explain that. And you have to think a second, well, do they have a string attaching them? You know, can you imagine how you would do that? Well, it didn't. Nowadays, we put it all in mathematical terms. We call it a gravitational field, but it's still the same problem. Why is an inverse square force? Okay, and this law was exactly the best law in the universe until 1915, when Einstein's theory came along. Einstein explained the 1 over r squared force and also explained deviations from 1 over r squared. And his theory was instantly accepted because these deviations were incredible. Nobody realized that these deviations could be explained by a new theory of gravity. Okay, such things as tides. Here's the Earth, here's the moon. Of course, this isn't the scale. And a tide pulling on the Earth and the moon gives rise to 2 tides per day, 2 high tides per day. Okay, so the bodies were spherical. Oh, why the heck don't we see a moon that's cubic? Why isn't our moon cubic? I mean, that'd be nice. Have a cubic rotating around. Why doesn't that work? Well, it turns out that gravity ensures that it won't work. It's pulling on it, and it doesn't work in detail. All right, 2 high tides a day. Don't worry. Now, I'm going to give you something that to explain Newton's second law. Right? This is Kepler's second law. Now, how do we explain that? Please don't write anything down. If you don't understand this, don't worry. But if you do understand it, that's great. Okay. How does, if you got a planet orbiting around the sun, the acceleration of gravity and its centripetal acceleration, m is the mass of the sun. Let m, little m, be the mass of a planet. The period is 2 pi, is defined as the distance divided by the velocity. That's the time, and we'll call it time p for period. And we can change this equation into velocity by multiplying it through, dividing by p. 2 pi r over p is the velocity of the orbit. And we say, okay, gm over r squared is equal to the acceleration. The acceleration was v squared over r times mass. That's from Newton's law. You have little m on both sides of the equation. That'll cancel. Okay, it cancels, and you're left with v squared is equal to gm over r. There's an r squared here, canceled 1r here. So this is what results. Okay, v is equal to 2 pi r over p. So that squared is equal to gm over r. Inverting this for period, period's equal to 2 pi squared r cubed, blah, blah. Constants, it's a bunch of constants. I'll label them together, call it k. And p squared is equal to r cubed. That is Kepler's law. Kepler had no explanation for it, but Newton explained it immediately. This is perfectly consistent with Newton's laws. Now, there wasn't any problem with that. And the answer is, okay. So, you can find all, you apply this application, you find that if you want to orbit the Earth, you have to be moving 7,850 meters per second. That is 7.8 kilometers per second to orbit the Earth at the radius of the Earth. You just imagine a rocket that is just skimming the Earth, and it's got to move that fast. Okay, that's pretty fast. Okay. 28,000 kilometers per hour is the speed you're talking about. Okay. Now, if you want to ask, how long does it take? Where do you have to put a satellite so that it orbits exactly once per day? Once per day, and that means that it appears to be overhead all the time. That's a geosynchronous satellite. Okay, sorry? All right, we have geosynchronous satellites that are at some point, and we send a radio wave to them, it bounces back. All right, so we have a lot of satellites like that, and you can find out how much you need from Newton's laws, how fast does a rocket need to escape, and all this stuff, and you know, all this comes out of Newton's laws, everything. All the motion of everything in the solar system is perfectly described by Newton's laws. Unbelievable. What an incredible breakthrough. This is an application of mathematics and describes everything that's known about the solar system. I mean, that is really unbelievable progress. All right. In his later years, Newton became warden of the mint. I think this was a gift by the king to Newton to say, well, if you're warden of the mint, that means you can skim off a little money for yourself. And all right, anyhow. But actually, he was warden for the mint because he worked all the time in alchemy. See, he believed that he could transfer lead into gold. That's neat. You know, that'd be nice to do. And a lot of people spent a lot of time on that, including Newton, because they knew gold's valuable and lead's not so valuable. They both weigh a lot, so let's work on it. And he tried to understand. Of course, that says how little anybody understood about nuclear physics. Well, you wouldn't expect him to know anything about nuclear physics 300 years ago. It was going to be a long time till anybody understood how it worked. So he tried to do it, and because he knew about how to do it, he was made warden of the mint, where he had to make sure that something that came in was really gold and wasn't painted lead or something. I don't know. Controversial with Leibniz over credit for calculus. For example, when you learned mathematics, you had notation for a derivative, or it could have been dr dt. Who knows this notation? All right, who knows this notation? This is it means the same thing. Derivative of r with respect to time. Second derivative of r with respect to time would be 2 dots, or second. All right, both of these are the same. This is Newton. He made this up. And Leibniz, German mathematician, made that up. Okay? So, you know, it's the same mathematics, but different notation. Okay, that didn't mean that he didn't fight with Leibniz. He fought with him all the time because he wanted credit for calculus, and Leibniz didn't want to give it to him. Okay, all right. But Newton was damn brilliant. And here's what he said. If I have seen farther than others, it is because I have stood on the shoulders of giants. That was his phrase. He stood on Tycho Brahe's and Kepler's data. That was primarily what he used to understand what was going on. Now, Alexander Pope, a very good poet, when Newton died, he wrote a little poem. Nature and nature's laws, what lay hid at night, God said, breakthrough, had just been affected by Newtonian mechanics. It was amazing. And so the world changed totally. I've got to emphasize, this is an incredibly different world. You threw out all this garbage of the Catholic Church or Lutheran Church telling you how to do it. No, do it yourself. All right? The cosmos is constructed from mechanistic rather than geometric design. Mechanistic meaning it obeys calculus. This was, all these led to, all this science led to incredible breakthrough and the invention of the scientific method. It was that long progression that led finally to Newton. Physics, not mathematics, is the key to unlocking the secrets of the universe. And the confidence of, after Newton, fundamental mechanistic framework is the way it works. Now, this is also incredibly important for our government. I don't think you realize that our government led support to the Enlightenment movement. This was incredibly in favor. This was how the intelligent people thought at the time of the French Revolution and then the American Revolution. The people who wrote our Constitution were all Enlightenment scholars who did not want to let religion come in and tell us how to do it. We are going to do it ourselves. And the mode of this new thinking, due to Newton's work, governed how we should govern ourselves. It just was a whole new way of doing things and incredibly important. Okay, gee, I finished. This is an incredible journey that led to the invention of the scientific method. And I cannot emphasize enough how powerful it really was. People afterwards would investigate everything. Investigated light. How the hell does light work? How does anything work? And they realized that, well, hell, let's be like Tycho Brahe and collect the data. Collect the data, and maybe eventually we will understand what's going on. And so the scientific method, which did not exist prior to Newton's coming, or all this came, was motivated by great thoughts in astronomy. Of course, we know that geocentric cosmology, heliocentric cosmology is not right. Heliocentric cosmology is an approximation that is, it's been replaced by something else. But at the time, it was the best theory around. And it didn't have, instead of 80 circles, which you had to specify, Newton had to specify one number, the inverse squared nature of the law, which he didn't understand. That's the only free parameter in his theory, one number. And of course, that's a much better theory because it predicts the motion of these things incredibly accurately. We send rocket ships to the moon, to Mars, and it gets there incredibly precisely using Newtonian theory. Now, if you know anything about our GPS system, GPS is the system of clocks that orbit around. A system that sends out beacons saying what time it is, or sends out a beacon that tells me this is a certain time, and all the clocks are exactly the same. That requires very, very precise clocks on these satellites. And they all have, and your calculator, you may not realize this, your calculator includes, it knows how to include the effects of general relativity, Einstein's theory. Your calculator, boy, doesn't look so brilliant, but it includes, it's calculating away, and because general relativity turns out to be an important issue for measuring what's going on with the clock signals coming from the satellites. Newtonian theory is very accurate, but general relativity is super accurate. Okay. Now, you say, well, Newtonian theory is wrong because it's been replaced by Einsteinian theory, but wrong only in the sense of if you're going for super, super accuracy, it's wrong a little bit. But boy, is it accurate when you talk about the orbit of, I'll take it, yeah.
Okay.
Thanks. Thank you.